We now come to one of the most important definitions that we will have all semester long, namely the definition of the supremum of a non-empty set. So to get started, let's look at the definition. We're going to let S be a non-empty point set. And just to remind you, what that means is that S is a subset of the real numbers, and S is not equal to the empty set. If we can find a P inside the set of real numbers with the properties that, first of all, P is an upper bound for set S, and second of all, P is less than or equal to U for all upper bounds named U of my set S, then we're going to call P the supremum of the set S. And we're going to write P equals SUP of S. It is traditional to pronounce this as sup S. So P is equal to the sup of S. It is important to also note that the sup of S is often called the least upper bound of the set S. And some people will write this as LUB of S. But sup S is the more traditional notation, and that is the notation that we will be using for the supremum of a set. Now, I want to look at what does this mean geometrically. So let's think about that. So geometrically, what does P equals sup of S mean? So let's think in terms of drawing a number line. So let's see, here's my number line, and I'm going to just kind of say we've got some sort of mess over here for S. So here are elements of the set S, and I clearly have an upper bound U. For my set S. And now what I'm going to do is I'm basically going to put in, and let's put it in this color, something that I'm going to label P. And P is basically going to live here. So P is going to be the sup of S. Now what that basically means is if I pick any upper bound, so here's an upper bound called U hat, here's another upper bound, U tilde, P is always going to be less than or equal to all upper bounds of S. But we also know that P is an upper bound for the set S. And so what that means is if we zoom in on this part of the number line, so let's look at that just a little bit closer. Here are some sets of S, so here are elements of S. And my handwriting is letting me down just a little bit, so let's fix that up. Elements of S. And I want to be thinking in terms of that sup. So here is the sup of S. Now what this means is that clearly no element of S can lie out here. In other words, there's no element of S that is bigger than P. So there is no S inside set S such that S is bigger than P. because otherwise P would not be an upper bound. But on this other side, I want to think about that as well. So let's look at this side. So what about over here? So let's think in terms of little delta balls. So here's my number line, and here is P, which is equal to the sup of S. And what I'm going to do is I'm going to think about, what if I have some A down here? So I'm going to let A be some number that is less than P. Now, if P is the sup of S, this tells me that A is not an upper bound for my set S. And what does that mean? That says there exists at least one little s inside set S such that A is less than S, because A is not an upper bound for S. And S, of course, has to be less than or equal to P, because P is an upper bound. So this inequality is because A is not an upper bound. If A were an upper bound, then P would not be the least upper bound. And this inequality here is because P is an upper bound. And we know that A is not an upper bound because P is the least, the smallest of all of our upper bounds. Now, I want to go on for just a little bit more about what this means in two situations, putting in the idea of some delta balls. So continuing to crunch on this definition, I want to think about this. So we've got our number line here, and what I know is that here is P, and P is the sup of some set S. Now, if P is actually inside S, then I'm going to put a big block there saying that it's inside S. What this means is that P is actually going to be the maximum element inside the set S. In other words, P is inside S, and for all little s inside set S, P is bigger than or equal to that little s. But what happens if P is not inside S? Well, let's look at that number line. If P is not inside S, then we've got P sits here, and P is not inside S. I know that P is the sup of S, so I know that P is an upper bound for set S, and I know that if A is less than P, then A is not an upper bound for set S. So what I'm going to do is I'm going to look at a little delta ball about P. So this is a delta ball about P. And in particular, P minus delta is strictly less than P. And so P minus delta is not an upper bound for set S. So what does that mean? That means there has to be an S inside S in this area here, between the end of the delta ball and P, because P is not actually equal to S. So what does this say? This says every, let me think of it as a half delta ball of the form P minus delta up to P contains at least one element of the set S when P is not inside of S. That gives you some good ways about thinking about the supremum of sets.